So we're still mostly doing a kind of consistency checks, not necessarily explaining all the processes, but we are trying to fit things into the observed structures, phase speeds, and so on. So we saw there is a fast moving sea level pressure signal that goes off as a Kelvin wave. Then there is a slow mode that is going with the convection. So why is convection moving at all? Why isn't convection pegged to one place? That's a question, and that's related to the idea of surface flux feedbacks. So if you remember, surface fluxes, sensible heat flux, function of a drag coefficient, wind speed, and the temperature difference across the atmosphere and the ocean, or land and ocean. Latent heat flux depends also on coefficients, wind speed, and difference in humidity across the interface or the land atmosphere. And we have the vertical exchanges of heat flux, which can be written in terms of vertical velocity, stability, and related to the heating we have, where of course we wrote S in terms of n squared, the Brunt-Väisälä frequency, and those can be related. The main idea here is something called WISHY, wind-induced sea-air heat exchange or surface heat exchange, because it can also happen over land or in the coastal regions. And the idea is very simple. If you have a background basic field where you have easterlies and you have the phase propagation happening where the disturbance is situated in an easterly background flow. So if you have rising motion at the convection hitting the ceiling and coming down on the eastern side, converging back into the convection, this is going to enhance the basic easterly flow. So the wind speeds are going to increase on this side, and this dependence will tell us that that's going to enhance the surface flux anomaly. Whenever you say that that is heat loss from the surface, that is going to feed the atmosphere and create instability or change in vertical stability. On the other side, you have westerlies, which oppose the basic flow of the easterlies and weaken the surface winds, and by the same token, you can see here enhanced winds and weakened winds. You have reduced surface flux. So you can see here you have basic plus U prime associated with the wave. Here you have U bar, that is the basic flow. Okay, so that gives you enhanced flux from the surface and feeding the atmosphere on this side, and loss of reduced surface heat flux on this side, which makes the convection shift eastward. Okay, this was proposed first by I think Charney and somebody. Later on it became very common with David Nealon, and maybe it was Kerry Emanuel who first proposed it. Please check it. Okay, so it's a very basic idea, and it doesn't necessarily explain then how do you lift the moisture from the surface to the free troposphere necessarily, but it does give you a simple explanation about how you can make the convection propagate eastward. The other idea is called convective instability of the second kind. The first kind is just the thermodynamic instability, where if you have warm SSTs, then you reduce the pressure and you create a potential instability. In the instability of the second kind, you are going to basically add convergence and circulation response to excuse me. And that can be done now using the idea of the vortex stretching. So we saw the vortex equation before with the tropical scaling of 10 to the 7 meter and Rossby number less than 1. That was our vorticity equation, where you had relative vorticity and the planetary vorticity, and we wrote that approximately as minus a dot times divergence of v. So that's relating the convergence and divergence to the stretching or compressing of the relative vorticity. And you can also think of it as cyclonic flow that's going to create convergence and create vertical motion into the air column. So that's one way you could lift moisture. But here, this is not talking about the surface fluxes at all. This thinks of surface as just dissipating momentum in this surface convergence, the frictional convergence that is dissipating momentum and allowing the Ekman pumping to pump moisture. And that goes to this figure we looked before, where we can lift a parcel to a small distance here to reach saturation, whereas you need much more energy to lift here. And if you are to the left of this, then lifting is not going to give you saturation at all. Okay, so CISC in this sense, the convective instability of the second kind, doesn't rely on surface fluxes, and the surface flux idea Vichy is not relying on the convective instability and the circulation. So obviously neither is complete, and now there are newer idea of wave CISC, because the scales that can be explained by CISC are, I think, too small compared to the observed scales of convection and so on. So again, what I said before is that these are kind of theories being fit to consistently explain what is observed, not necessarily from the large-scale first principles. So they are somewhat incomplete. But we will add a third idea here about how spatial variation of the basic state itself can also provide the explanation for the fast and slow modes that we are trying to explain here. Okay.